Stat A, (9.1.1) intro to confidence intervals. Day 1. Now, I see a lot of people who are just focused only on their computer, where none of this right here is when we're in notes. It's dealing with your computer. Um, you're telling me that you don't care, that you're more focused on whatever else is in there. Your eyes are at your computers. You're moving things on the computer. That's what your focus is. Some of you, very few of you, actually use the computer or for the notes. But there's so many of you that are doing it. So I'm letting you know right now, I am aware. And what you're telling me is you do not care about the material. And some of you are struggling. When it came to the material, you don't know what to do when we had the assessment. And tell you the truth, with certain accuracy, it's mostly those students who are not paying attention to the notes at all. So you're going to be off in college very soon. Some of you are going to be barely passing by the wit of your eyes. Some of you are probably not. And a lot of that comes down to the focus you're giving. So do know, when you're doing this, when you're on your computer and you're not paying attention to notes, we can tell. So the main thing that we're talking about here, so of course we're talking about, we know the sampling distribution of sample proportions. We know that if we are talking about, so we know we do SIN, we want a sample that is random. We want to know that our sample size N is less than 10% of the population. And then we want a normality check, which is the success and failures, or in proportion, sorry, is N times P should be at least 10, and N times 1 minus P should also be at least 10. And if all three of these things are true, then the sampling distribution is approximately normal, where the mean of P hat is P, and the standard deviation of P hat is the square root of P 1 minus P over N. Okay? So we're only going to be focusing on proportion. So that nearly normal condition where N is greater than or equal to 30, or the population is already normal, when we're talking about mean, to tell you the truth, we're not going to be able to cover that within the rest of this course. All right, we don't have enough time left in the school year to cover the inference on sample means. So all we're going to do from the rest of the school year is talk about inference on sample proportions. So that's what we're doing. So this is basically everything that we had. That was half of what we did on the previous assignment, right? The previous unit right there. That's half of it. But what if we don't know P, the parameter? All right. So the question is, what is, remember, P is the true proportion. Sorry. And I'm gonna put brackets around true. The true proportion of blank, the population, whatever the population is, who and blank are successes, however we define a success. We don't know this. This is unknown. We don't know P, the true proportion. We don't know the parameter. In the previous unit, I gave you that answer. This is what it is. But what happens when we don't know? That is the whole purpose for statistics. This is called, we're going to utilize inference. All right, we're going to utilize inference. We don't know what it means, so we're going to infer what it means, what it is, and so we're going to use a sample proportion, p hat, to infer what is the parameter, P. However, we can only infer an interval prediction as samples vary. So what I'm trying to tell you is every sample you take is different. So just because you got in your sample 26% of students say we need, or 26% of students say school needs to start later, or like 80% of students want to start school later on in the day. That doesn't mean that 80% of the entire school wants to start later in the day. That's 80% of your sample. Now, based on that 80%, well, first off, that 80% should be unbiased. That's why we say it still needs to be random. What is the likelihood of what is the true parameter? What is the true proportion of the entire school? So what we're going to do, so once again, we're going to have our conditions. Our condition checks are still going to be in there. S-I-N. Same conditions. But once I'm going to write this again because yes, it's that important. The sample is random. N is less than 10% of the population. And talking about normality, here's where it's different. We don't know P. So we're going to check N times P hat. That needs to be greater than or equal to 10. N times 1 minus P hat must be greater than or equal to 10. So this is the sample successes. And this is the sample failures. Now, it's just a little difference in the vocabulary, but we're not talking about N times P hat represents the number of successes you got. So basically, this number right here is X. That's X, the number of successes that you got. It's not the predicted, because we don't know. We don't know what it is. And if this is true, then once again, we can say approximately normal. And we're going to use the mean, and we're going to use whatever P hat is from our sample. And for the standard deviation, we're going to use the square root of P hat 1 minus P hat over N. Now notice slight little difference. I'm not using P, I'm using P hat because we don't know what P is. But there's something also to note that this is actually called the standard error. Because it is not the standard deviation. The standard deviation is from the population. Because we're estimating what it is, we call this the standard error and not the standard deviation. Because it's based on a sample proportion. It's based on a sample statistic and not on a parameter. If we knew P, when we use the actual value of P, this is the standard deviation. But we're going to call it from here on out basically the standard error. I might say back and forth standard error, standard deviation, and for the most part they mean the same thing. But standard error is the more appropriate word. All right, so once we know that, just like we did in our do now, we can kind of create a normal model. Here's p hat, and then we can make our markings. And, bless you. And, you know, we add our standard deviations, and we know that there's about, and I'm only going to focus on this one right here, this, about 95% fall between p hat plus 2 standard deviations, and this is p hat minus 2 standard errors. Sorry, 2 standard errors, not 2 standard deviations. As we did in our do now, this creates an interval. And that interval would be p hat minus 2 standard errors, comma, p hat plus 2 standard errors. This has a special name. It's not just any interval. We call this a what again? What is this interval called? It's in our title of our lesson. Confidence. And so, but what, that interval between here, 95%, and using the normal model is called a confidence interval. Now, this confidence interval is, and I want you to note something, there's a connection right here between the standard errors. All right? There is a connection here between the standard errors. So, if I make m bigger, then the standard error becomes what? Smaller. Well, the standard error becomes smaller. So, as a result, as n increases, the interval what? The interval decreases, the interval narrows. Yeah, and it's more narrow, wider. So smaller n would be wider interval. Bigger, wider. It just, I think that when we talk about intervals, we usually say narrower and wider. Also, this is 95%. So if I wanted to do 99.7%, if I was going to do 99.7% interval, what do we notice about that interval? This is for 95%. This is called my confidence. So, as confidence increases, if I want to be more confident, what's going to happen to the interval that I'm going to predict? It's going to be wider. Yeah. So think about this model right here. So if I want to have more confidence, instead of being 95% confident, I want to be 99.7% confident. My interval, my net is going to get wider. My interval will widen. Okay. Last thing. How do we interpret a C% interval? Now, notice I said C% because C is like right 95%. Right now we're doing, so that C would be 95. So in a 95% interval, like how would we do that? It is a statement, and the blanket statement is always the same. We are blank, which is C%, which is the 95%, confident that the true, and I like to write the word true. Some statisticians don't like to write the true proportion because the proportion of the population is the true proportion, so it's kind of redundant. I do want to note that, but I like to write the word true. The true proportion of blank, the population, who blank, whatever is defined as our successes, you got to use the context of the problem, is between blank and blank. This first blank is the lower boundary, and the second blank is the upper boundary. Now, I'll change this to be A and B later on, but basically it's the upper boundary and lower boundary. So whatever answers you get from here, you just say between there and there. You'd also, something to note, you don't have to change it into a percentage. In the do now problem, it changed it to 0.66% and 2.14%. My preference is that we just keep it as the decimal proportion. So we would say between 0.0066 and 0.0214. We'll just leave it as those decimals. And that's as far as we're going to go today. Again, we're going to be reiterating the same thing. I'm going to keep, so tomorrow, I'm going to go further into what we just said right now. All right, so don't worry. It takes some time to get it over. You're not going to grasp it in one day. This sentence, though, right here, you're going to keep saying it throughout this entire unit. Basically, every day, this sentence right here, you're going to have to write it out again and again and again. We're going to change the confidence intervals. We're going to change the sample sizes. We're going to change the context. But the problem still becomes the same. That's what I have for you today.